Hello everyone, welcome back to Mathematical Statistics. So today we will continue our discussion of multivariate random variable by talking about the notion of independent random variables. So we have discussed part of this material earlier in the lecture slides for chapter 4. So for today we will just try to clarify a few more additional details. So the definition goes as follows. Let x1 and x2 be random variable and they have marginal CDF f1 and f2. And suppose that jointly x has joint CDF f, then we will say that x1 and x2 are independent if and only if for all values of x1 and x2, the joint CDF can be written as the product of the marginal CDF. So, in summary, probability that x1 less than equal to x1, x2 less than equal to x2 is the same as the probability that x1 less than x1 times the probability that x2 less than equal to x2. And we say that two random variables are dependent if they are not independent. So let us first describe the notion of, characterize the notion of independence for discrete random variables. So the independence of discrete random variables will be characterized in terms of their probability mass function. So we have x1, x2 that are discrete and they have marginal PMF, P1 and P2. And suppose that they have joint PMF together, the pair have joint PMF P, then we say that they are independent if and only if for all values of x1 and x2, the joint PMF is the product of the individual marginal PMF. So let's go back to this definition here. The definition here is in terms of the CDF. And the characterization here is in terms of the PMF. So we have to show that this characterization is equivalent to the definition. So our proof goes as follows. Suppose first that the condition is true. That is, this condition is satisfied for all x1, x2. Then as we see, because by the definition, the joint CDF is written as a sum of PMF, which is going to go here. Therefore, by the rule here, the product of the marginal, we can write as the product of the marginal PMF. And then now, because this is double sum, we couldn't just move the sum P1 out side here and write as a summation of y1 less than x1, P1 y1, and then summation of y2 less than s2, P2 y2. But this is nothing more than f1, the cumulative, the marginal cumulative for x1, and the marginal cumulative for x2. And so that satisfied the condition earlier. That is, the joint P, the joint CDF is the product of the marginal CDF. Conversely, suppose that the joint CDF is indeed the product of the marginal CDF. Then we need to show that if this is true, for all x1, x2, we want to show that this implies that P of x1, x2 equal to P1, x1 and P2, x2. And the argument goes as follows. So for any value x1, x2 with p x1, x2 bigger than 0, there must exist an epsilon bigger than 0, such that the property mass function for x1, x2 can be written in terms of this quantity. So this is similarly in the univariate case. In the univariate case, p of x, if p of x is bigger than 0, then there exists an epsilon bigger than 0, such that p of x is fx minus f of x minus epsilon, which is the same as the probability that x minus epsilon less than x less than ax. So in the bivariate case, it will be the same idea. You just need to have the joint, kind of like the difference of the joint CDF. But as we see earlier in the last video, that this probability here can be written as this form. So let's try to go back and see that. I think that is earlier on. Let's see here. That is earlier on slide, I suppose, slide 4 or 5. Yep. So this one. So slide 6. So let me just put that up. We want to go to, yes, here. So that is slide 6. But because of this condition, the first term here will look like f of x1, f2 of x2. This second term here will look like f1 of x1 minus epsilon times f2 of x2, and so on and so forth. And so by expanding out the product, you will get that. Let's just erase this just so we can see clearer. You get that this is equivalent to this product difference by multiplying our terms. But this difference here is by the univariate case. This is just p1 of x1. This is p2 of x2. And the key reason why this condition is true is just because our random variable is discrete. So there must be a value for which the joint CDF jumps. Okay, so let's now turn our attention to characterizing independence of continuous random variables. So once again, the idea is similar. You would characterize the independence in terms of the joint PDF. So in this case, if you have x1, x2 that has joint PDF f, and x1 and x2 have marginal PDF f1 and f2, then they're independent if and only if for all x1 and x2, the joint PDF can be written as the product of the marginal PDF. And so the proof is similar to the discrete case, so we will not belabor the point. But in particular, for example, if the condition is true for all x1, x2, then you can write the joint CDF as a double integral. Each of the integrand can be factored out. You can then move it around, and you can write this as the product of the marginal CDF. The other condition is once again the same, but in case of, because of the double integral, you see that the CDF, the joint CDF, is written as an integration of the marginal of the joint PDF, and so therefore the joint PDF can be written as the derivative partial derivative of the joint CDF. So in the sense, f of x1, x2 can be written as the partial derivative of the cumulative with respect to first, say z1, and then z2, and then evaluate at x1 and x2. Evaluate at z1 equal to x1 and z2 equal to x2, which is what we did here. And then once again, by the fact that you can take the product, you can write out this joint CDF difference as 2 marginal CDF, move the epsilon 1 out, move epsilon 2 out, and then take the partial derivative on both sides to get the product. Okay, so generalizations of these ideas to 3 or more random variables are straightforward. So for example, if you have a bunch of random variables, then they're mutually independent if for all values of x1, x2 to xm, the joint CDF can be written as the product of the marginal CDF. So in the case of when they are discrete, then that condition can be simplified further to saying that the joint PMF is the product of the individual PMF, and the joint PDF, in the case of the continuous, is the product of the marginal PDF. Okay, so let's see a few quick and dirty examples. So we have this random variable y. This is example 5.10 in textbook. So f, y1, y2, so y has this joint PDF that can be written as the form 6y1, y2 square. And this is support inside the unit square. So we're going to show that y1 and y2 independent. And so we just have to verify the condition that f of y1, y2 is the product of the marginal. And so the marginal is easy to evaluate, f1, y1. You just have to evaluate with respect to the second argument over the range from 0 to 1 for the y2. And that is a simple exercise in integration to give you 2y1. And similarly for f2, y2, integrate with respect to, this one should be dy1. That's a typo. This should be integration with respect to y1. And once again, that turns out to be 3y2 squared. And so the product gives you 6y1, y2 squared, which is what you have here. So this result here can be generalized to yield a quite useful result. See theorem 5.5 in your textbook. In particular, if you have a continuous random variable with joint PDF f, then if f satisfied the condition as follows. First is that f is positive only when x1 and x2 are in some rectangle from AB times CD. So in the previous case, we have in the example 5.10, we have that the PDF is f(y1, y2) is 6y1, y2 squared, and then for y1 in 0, 1 and y2 in 0, 1. So the first condition is satisfied. And the second condition is that there exists function g and h such that you can write f(x1, x2) as gx1 and hx2 for some function g and h for our x1, x2 in that interval, in that rectangle. Then under these two conditions, x1 and x2 are independent. So let's try to verify this result. So as I said, this result provides a quick example, a quick check that this one is independent, because you can write this as h, you can write h as maybe like 6y1, and then g maybe like y2 square. And as I said, it is inside the square. So the proof of that result is simply as follows. Due to the way we defined it, we define f1 of x1 marginal to be the integration of f y1 y2 of dy1 dy2. So in that sense, f1 x1, if you assume the condition is true, that fx1 x2 is f1 is equal to g x1 h x2, then basically f1 x1 the marginal can be written in terms of this integration. And similarly, f2 x2 can be written as this integration. Now here we have used h x2. But the key point is because f x1 x2 is supposed to be a PDF, a joint PDF, the integration over the whole region should be equal to 1. But because of the way that we can factorize the product, that can be written in terms of these two integration. So the product of this integral should be equal to 1. And so therefore, fx1 x2 by default is gx1 times hx2. But if we now multiply by the integral, due to the condition of this integral is this product here is equal to 1. And so this is simply f1 of x1, as we say here. And this is f2 x2, as we say here. And so the joint PDF is the product of the marginal PDF. And so we have the result as claimed. So let us see another example. So this is example 5.12 in your textbook. So we here say here y is y1, y2 has joint PDF of this form. So if you remember, the joint PDF here looks as follows. You have this line y1 equal to y2, 1, from 0 to say like 1. And so the joint PDF is defined in this triangle here. Then you can easily see, suppose you take a cross section. Suppose you take a cross section here, this point here, and you measure to the right. So f2 y2, so this is the value of y2. You see that f2 y2 is positive because of this part here. Similarly, f1 y1 is positive because of this part here. But here, the joint PDF is supposed to be 0. And so therefore, y1 and y2 cannot be independent. So in fact, because there exists any value y1, y2 in this area has joint PDF 0, but have marginal PDF bigger than 0 for both y1 and y2. So therefore, y1 and y2 cannot be independent. So we will now move on to the topic of the expected value for the functions of random variables. So we now formally define this notion of expected value for functions of multiple random variables. But note that we have used many of these ideas before when we're considering, for example, the expectation or the moment generating function of a set of independent random variables. For example, earlier we see that the binomial NP can be written as x1 plus x2 plus dot 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 plus xn, where the xi are binary. And using this fact, we were able to show that the expected value of x is equal to n times the expected value of the x1 equal to np. So we have done many of these things before. So let's just give them a formal justification. So let x be a multivariate random variable, discrete, and suppose that x has joint PMF, px1, x2 up to xm. Then for any function g, so g takes m arguments and return a real number, the expected value of g x1, x2 up to xm is simply the sum of the function g weighted by the joint PMF over all values of x1, x2 up to xm for which the joint PMF is positive. Similarly, if you have a continuous multivariate random variable and you have a joint PDF, then for any function g, you just replace the sum by integrating with respect to the joint PDF. So one thing that we have tried to avoid talking about in this class is what happens when you have, say, x equal to x1, x2, x3, say, and x1, x2 are discrete, and x3 is continuous. So how should you define, say, expected value of g of x1, x2, x3? And the answer is a little bit more complicated, but heuristically speaking, it works just the way you want it to work. So we will not mention it too carefully, and so you will see a few examples later in this class where we do those kind of expectation or expected value. But for the most case, when your multivariate random variable is mixed, it works out just as how you would expect it to work. In any case, we have the following important, a bit simple results, but the main idea is that expectation is a linear operation. So the first thing is that if you have a multivariate random variable, then by taking expected value of c, that should be equal to c for a constant c. So what does this mean? Well, what this means is that suppose, for example, in the discrete case, the expected value of c is written as the summation over x1 up to xm of c times the joint PMF px1 up to xm. For example, in the case of continuous, you would replace that in the continuous case you say the expected value of c will be written as summation as the integration of c times the joint PDF. And so that is what we meant by this expected value. So this is another place where it is time to be a little bit more, say, careful. Whenever you see the symbol expected value, especially in the multivariate case, you always have to remember that what is the underlying probability talking about. So we always use the letter E for the expected value, but in many cases, we never really say explicitly whether we're summing things or whether we're integrating things. We just write E, and you have to understand implicitly what kind of operation we're talking about. In most contexts, we don't have to think too much about it. But on some occasions, sometimes we have to be a little bit more careful. So we will try to maybe mention that when it comes along. But usually, whenever you see E, implicitly there is some underlying probabilities floating around, just as you have to. So then the next thing is that the expected value of c gx1 up to xm, where c is a constant, you can then move the c outside of the expectation. So for a constant c, you can then move the c outside of the expectation. And then finally, the expectation is linear, so you have sum of functions g1, g2 up to g capital K. Then the expected value of the sum of g1 plus g2 plus gk can be written as the sum of the expectation. So in simple word, expectation of sum is the sum of expectation. So finally, we have already used this in chapter 4, but let us revisit it again. When x1 and x2 are independent random variables, possibly multivariate, then for any function g and h, the expected value of gx1, hx2 can be written as the product of the expected value of g of x1 times the product of the expected value of h of x2. And so you can see the book for proof, but it's quite simple. All it really does is just say that you can write because of the way you write the function, you can write it as integration gx1 hx2, the joint PDF, for example, in the case of continuous. And because of the way you can factorize this, you can write this as g of x1, h of x2, f1 x1, f2 x2, dx1 dx2, and so this can be written as integration of gx1, h of x1, dx1 times the integral of h of x2, or this should be g of x1, f1 of x1, h of x2, f2 of x2, dx2, which is what we have here. So as a quick example, earlier we see that if you have mutually random variables x1 to x4, then the MGF of the sum is the product of their MGF. So MGF of the sum is the product of MGF. And we see this earlier in chapter 4. Furthermore, for example, for something more complicated like this one, then you can say that this random variable here only depends on x1, x2, so you can move it outside. And this term here depends on x3 and x4, so you can put it outside. So that is why here we say that x1 and x2 are independent and possibly multivariate. But in any case, as long as you can write it as one function that only depends on the subset of the random variables, in this case, this one only depends on a subset, and this function here only depends on the other subset, then you can factor out the product of the expectation. So as a cute example, let's do this problem. Suppose I have x and y independent, uniform, and I want to know what is the expected value of x minus y. So we'll see many of these kind of examples later in chapter 6. But let's do a quick example now. So the expected value of x minus y in absolute value, you write out as the double integral, the function, and this is the joint PDF, is equal to 1, dx dy. So now you're taking the absolute value of x minus y, so we see that x minus y absolute value is equal to x minus y if x is bigger or equal to y, and is equal to y minus x if x is less than or equal to y. So in this case, for the first term, we see that it is y minus x as long as x goes from 0 to y. And then for the second part, it is going to be x minus y as long as x goes from y to 1. So x is bigger than y. Here, x is less than y. And now this is a simple exercise in integration, and so you get the answer to be 1/3. So if you have two uniform random variable, then on average, the distance from one another is 1/3. So now we will take a detour. So this material is never included in your textbook. It's not included in your textbook. But I think it is important enough that we should take a look at it now. It is unlikely to appear on your exam, so you can rest assured, but I think it's one of the most beautiful and yet simple result for an applied mathematician to know. So let's talk about it. And so that's the notion of convex function and what is known as Jensen inequality for expected value. So the notion of convex functions, one of the most useful concept, I think, in applied mathematics, or not even applied, just mathematics in general. So we will define convex function in a very simple case for the interval, but you can define convex function in general for, say, like other kind of sets, such as convex sets in general. In any case, for interval, let a less than b, a function f on the interval ab map the real line is a convex function if and only if for any two value of x and y in the interval, and for any constant t in 0, 1, then the function evaluated at the linear combination of x and y, so tx plus 1 minus ty, is less than t times fx plus 1 minus t times f of y. So you may say this looks like an abstract condition. What it really is, in simple word, is that the function, they said the line connecting 2 points on the curve of the function will be above that function. So here we have the point x1, here we have the point x2. The line connecting x1 and fx1 to x2 and fx2, so the line connecting x1, fx1 to x2, fx2. This line here has to be larger than the function in that integral, in that interval. So that is basically the meaning of a convex function. The line between 2 points on that function curve is above the function itself. So we now list two important properties of convex function. So we'll give an examples of convex function later in a few slides, but let's look at what the conditions there implies. So in summary, if you have f, which is a function from the interval ab to r, and f is differentiable, then f is convex if and only if for all value of x and y, the function evaluated at x is bigger than the function evaluated at y plus the Taylor expansion. So you remember from your calculus class, fx is approximately fy plus f prime evaluated at y times x minus y. So this here, this condition says that if a function is convex, then not only is that it is approximate, the function has to be strictly larger than that linear approximation. And the proof is, I think, quite simple. So if you have the condition, let's write it out, f of tx plus 1 minus ty is less than t of fx plus 1 minus t of fy, then by rearranging this inequality, you should get this condition. And as you can see, if you multiply t here, that becomes t fx is bigger than t fy, but then you minus fy, so that becomes 1 minus t fy. And so you move this 1 minus t out here, or t minus 1. So t, that becomes t minus 1 fy. And so you move it this to this side again, then that becomes 1 minus t fy, and it's bigger than this term. And so if that is the case, that is, you have this inequality, then by taking the limit as t goes to 0, you have fx is bigger than fy plus the limit as t goes to 0. Because this is true, this condition is true for any t. So you can actually take the limit. And so we will write out this as y plus t x minus y. And so the derivative, so this limit should become the derivative at y times x minus y due to the x minus y here, and what you have in the denominator is t. So that condition is true. So if f is convex, then f is bigger than the linear approximation. The converse is proved similarly. So suppose f satisfied this condition for the linear approximation. Now you have two values, let's say x and y. So suppose that f satisfies this condition for any x and for any z. Now you have two values x and y. Then you could just let z be the linear combination of x and y, just as what we have earlier before. Then using this condition here, we have fx has to be bigger than fz. And using the same condition, with now x replaced by y, fy is also have to be bigger than this linear term. But now if all you have to do here is now if you multiply this first term by t, so if you have two inequality, then you say that t of fx, multiply this by t, multiply this by 1 minus t, plus 1 minus t of fy is going to be bigger than t of fz plus t of f prime z times x minus t of f prime z times z, and then plus 1 minus t of fz. So together you will get fz itself, and then plus say 1 minus t f prime z of y, and then minus say 1 minus t of f prime z of z. So this sum, it will be equal to fz plus tx 1 minus ty plus f prime z times tx plus 1 minus ty, but that is just simply z here, f prime z times z, and then once again you have t and 1 minus t for t and 1 minus t for f prime z, and so minus f prime z times z, cancelling out, so you get this inequality as desired. So now we have seen that convex function has this nice looking property, so that it is larger than its linear approximation. But we still do not know what a convex function is. So the following result is very useful for checking whether a function is convex. And the result is simply that if you have a function f from AB mapped to R, and suppose that f is twice differentiable, then f is convex if and only if the second derivative is positive. So this is a very useful result to check. If you have a function twice differentiable for whose second derivative is always positive, really bigger than or equal to 0, or non-negative, then f is convex. And the proof is basically based on a simple application of Taylor's theorem with the remainder term. So for example, fx, by doing this Taylor expansion at around the point x0, plus f prime x0, the first derivative, plus the second derivative, but now evaluate at the point x star between x0 and x, then because f double prime of x star, the second derivative, is always non-negative, So this term is always bigger than 0. So you have that this condition is true. And this condition, as we see earlier, is this proposition here. And so, like I said, this condition is a very useful condition for checking convexity. So, for example, x squared is convex because f double prime of x squared, or f double prime of x, in the case when fx equal to x squared, is simply 2. In the case of e to the power of x, that just becomes e to the power of x itself. In the case of 1 over x, it then becomes 1 over x cubed, which is positive also. In the case, so this function is convex on the real line. This function is convex on the real line. This function is convex on the positive integers. 1 over x minus 1 over x squared, 1 over x cubed. So this function is convex on the positive integers. And this function is convex on the positive numbers. So this function is convex on the positive numbers, and this function is convex on the positive numbers also. So why do we have to introduce convexity? Well, it turns out that convexity is a very powerful concept in expected value. Convexity is very useful when you combine it with expected value. And so we come up to change set inequality, one of the most famous and most widely used inequality in mathematics. So you cannot avoid change set inequality. In summary, suppose you have f, a convex function, then for all random variable x, the expected value of f of x is bigger than the function f evaluated at the expected value. So for convex function, the expected value of the function is bigger than the function of the expected value. Assuming that both expectations exist, and we generally have to assume that the expected value of x lies in the domain of convexity of f. So a function, so we'll only prove change set inequality in the case when f is differentiable, but the proof is very, very simple. In fact, for such a powerful result, the proof is so elementary as to belie its importance. But the proof goes as follows. Let mu be the mean of x. Then, because the function f is supposed to be convex, so then for all x, let's say in the domain of f, where f is convex, we see earlier that fx has to be bigger than its linear approximation. That's what we saw earlier in the proposition before. So if just in that case, we can say that f of the random variable x, whatever it is, because whatever the random variable x is, it has to take value in little x. F of capital X, the random variable, has to be bigger than f of the mean plus f prime of x minus mu. F prime times x minus mu. Now, by linearity of expectation, expected value of fx is bigger than the expected value of the linear approximation, because that's just trivial. And because expectation is linear, so expected value of f mu is a constant, you can move it out. f prime mu is a constant, you can move outside. And now expected value of x minus mu is just 0. And so you have expected value of fx is bigger than f of the expected value of x. A result that is very, very elegant. Or proof that is very elegant, I think. So let's see an example. So Jensen inequality implies because x squared is convex, that the expected value of x squared is bigger than the expected value of x itself, everything squared. So that is why the variance of x, we can define it as expected value of x squared minus expected value of x squared. Similarly, the moment generating function, expected value of e to the tx, has to be bigger than the exponential of t to the ex. So that is why, as you see, the expected value, if the moment generating function exists, then expected value of x exists. But expected value of x exists does not imply necessarily that the moment generating function exists. And that is simply a consequence of this one also. And furthermore, expected value of 1 over x is bigger than 1 over expected value of x if expected value of x is positive. So for example, let x and y have the same distribution and are independent, and suppose that say expected value of x is bigger than 0, then the expected value of x over y by independence can be written as expected value of x times expected value of 1 over y. But by this condition of convexity, that's bigger than expected value of x times 1 divided by expected value of y, which is bigger than 1. And so on average, x is larger than y. However, using the same argument with x and y swap, we can also conclude that on average, y is larger than x. So we have seen this kind of like example earlier in say like chapter 3, but this basically just says that the notion of the word on average is a very ambiguous word. So the expected value of x divided by y bigger than 1 means what? And I guess the answer is it just means that there are a bunch of values for which x and y is bigger than or equal to 1, and due to how the probabilities are, those values may have large enough probabilities that the expected value will be bigger than or equal to 1. But it does not mean that, for example, probability that x divided by y is bigger than 1 is bigger than 0.5. That does not mean this. Okay, so we will end here for today. For next lecture, we will now talk about the notion of covariance and correlation. And so I will see you next time. Take care, and please send me an email if you have any questions. Bye.